First, thank you for giving me this opportunity to talk about our work on the nanoparticles. That they are made of pentamers, so they are in the shape of tubes, and spherical particles, so they are somehow related to packing, but the packing that has been directed by nature. So protein cages, when we talk about protein cages, these are cages, spherical objects that they are made of proteins. So they are really important in nanotechnology because we can use them for designing vaccines, for drug delivery, for gene therapy, and the ability to be able to control their size, their morphologies is really important. Then we could make a bigger particle or a smaller particle based on what we want to put inside them. So the first protein cage that comes to mind is viruses, because we learn things from the nature. So viruses are like this. Here, it's hard here. Now you could see viruses here. So they have opposite symmetry. So they are made of 12 pentamers and hexamers. So Kasper and Klug, they proposed the first mathematical design principle for them. So if you open the lattice of it and put it on 2D lattice, so you see that it's a hexagonal lattice. So the icosaedral net, open it, that gives you that lattice. So if you cut, that's this, so you put it, then you just cut the icosaedral lattice, wrap it up around, and that gives you the cage. When you get the cage, something that, so it depends which two hexagons you connect to each other first, and then you repeat and you cut and you wrap it so you could get a bigger particle. And something that is important here, you see that the proteins are sitting in the corner of the hexagons and pentagons. So the position of the protein is being, you find the position of protein is this approach. So here is a better example of it. This is a pericotavirus. The pericotavirus is made of trimers. So these black triangles show the trimers, that they are made of 3 monomers. So if you do the same thing, if you wrap it, so you see that the triangular tiling predicts the correct position for monomers. So each monomer is sitting on a corner. But if you look at the dual of this lattice, which is pentagon and hexagon, again, the same thing is happening. The proteins are sitting in the corner of the hexagon and pentagon. So you could either use triangular tiling or hexagonal tiling. In both cases, you are predicting the correct position for monomers. So monomers are sitting in the corner of the ties that are there. So the Kasper Klug works for lots of viruses, and they can capture the position of proteins. Another degree of freedom that comes from the hexagonal lattice is the gyration. So in the hexagonal lattice, so what you could do, you could rotate each hexagons, and then that kind of creates a small gap between the 3 hexagons. But again, the rest is the same. So we have 6-fold symmetry. We choose 2 hexagons, connect them, then an equilateral triangle, then 20 of them, cut it up, wrap it up, then you get another protein cage. But over here, you have a small gap. And it has been observed. So this is the AaLS, Lumazine Synthase. It's a protein in every cell. They are available because they have to catalyze the production of vitamin B2, and they are made of monomers. 5 monomers form a pentamer, which is the shape of a pentagon, and 12 of those creates a cage. And here, if you can see that between 3 pentamers, there's a small gap here. So this can be, so for these ones, we need a gyrated tiling to predict the position of the protein and to be able to predict the gap that is here. But this is a nice protein. So that's what the nature does. 12 pentagon, nice, beautiful, but we could mess with it. And if we mess with that protein, it can form tubular structures. There is a collaboration with the Yuska's lab in Jagiellonian University and his postdocs Lukasz. What they did, they formed these circular permutations proteins. So we have the Y type, which is like that. So what they do, they cut the protein from inside, and then they connect the outside of the protein. But there are 2 positions that you could make a cut. One, you have 156 amino acids, so you either cut at 84th position or 119th position. So the reason for that is that, so now the outside is closed, but inside is open, so you could put something inside the cage and then deliver it to the body. So over here, so we have 2, we have CP84 and CP119. CP84 is boring. It again forms that 12 pentamers, same thing, gyrated lattice, nothing interesting happens there. But CP119 is the most beautiful protein, as you can see. It forms two types of proteins, two types of tubes, which we call them flat tubes and twisted tubes. So flat tubes are quite, we call them flat because they are really like a nice shape around the tube, but the twisted ones are twisted. And they have a gap as well. So the question is that why we are seeing these two tubes? Is it possible to see something else? Or why them? So that was the main question. So they came to us. So what we did, so if you color the protein, so if you look at the first stripe of pentamers, so we connected, there's a red one, there's a blue one, and then there's a green one. So we say that the helicity number is 3. So you need 3 stripes of pentamer to form it. And then if you look at on each stripe, so you see that 2 pentamers are binding together, but the monomers are interacting with each other by the help of an arm. But between 2 stripes, the interaction is happening without help of any arm. So over the stripe, these are binding by help of arm, but this is without that. So we have 2 types of interaction that they are happening. So which we call them, the one we have a helicity vector or helicity number, so we go 3, and the periodicity number. So we say that if we call this a diagonal of pentamers, so we have 1, 2, 3, 4, and the 5th one comes again on top. So the periodicity number is 4, the helicity number is 3 for the one that they are seeing in the nature. But is it the only one? So what we could do now, simple math. So we say that if I want to have this helicity number and H, periodicity number and P, and the vector that kind of gives us the shift H. So we know H, we know this, so what are the mathematical relationship between them? So we could have A as a function of NH and P and B. So B shows that how much you are going up, and then based on that and what NH and NP you want, you could find A, that how much you have to shift that side or this side. So then now we have that. So we set up what if helicity number is 5 instead of 3? What if it's 5? What happens? So then we get this shape. If you look at the position of proteins here compared to the wild type one. So you see in the wild type one, the arms are like this, but for that one, the arms are flipped. It's not, you cannot just do that. These are 3D protein objects. You cannot just simply flip a protein and then hope that it does the same thing. So it doesn't do the same thing. So it shows that this is not possible, because to do that, you need a flip in the arm position, which is not feasible biologically. But other helicity, what about number 2 and 1? Arm-wise, they are okay, but why we are not seeing them? But for bigger one, helicity 4, 5, 6, beyond, we see that, okay, because there's a flip, so they are not happening, but there are lots of possible cases. So if we just do math, I mean, the black dot shows the case that is not feasible, but the green dot shows the case that it is feasible, at least regarding the position of arms. But why we are not seeing them? Why just 3 and 4 is the most favorite one? So what we did here, we looked at the contact and the radius. By contact, I mean we have 2 pentamers next to each other. If they are like this, we say 100% interaction. If it's lower, 80%, 70%, 60%, like how much they are covering their interaction. The contact, you are measuring that percentage of contact between 2 pentamers. Radius, we are looking how big is it. So it's as it gets bigger, it gets less stable. This is kind of like biological object. It wants to be as small as possible to be more stable. So when we look at the contact, so we saw that as it gets bigger, the contact gets better. So these small ones, they have the worst. The red dot shows the 3 and 4 case. As it gets bigger, contact is better. For the smaller one, contact is worse. And the same thing for radius. For this part, the radius is bigger than this smaller part. So we could say that maybe these are too big, so nature doesn't want to do them. But among these small options, why 3 and 4 is chosen one now? Why? I mean, of course, here has a better contact, but these ones are smaller. So why 3 or 4 is chosen, but not these small ones? So over here, if we look at the angle between 2 pentamers now, in the wild type, when we have 12 pentamers, the angle between 2 pentamers is 116. In 3, 4, the angle between 2 pentamers is 131. In these small cases, the angle is even sharper than the wild type. So we are getting a sharper angle than wild type, and we are having a less contact compared to 3 and 4. So it kind of shows maybe why this is the most favorite one, because at least the iron doesn't need to really too much, press them too much close to each other. So an idea why this is the favorite one. Another thing that is very interesting, why we are seeing that helicity, why it's going up. If you look at the structure of a pentamer, so yeah, we have the first pentamer and then we go 1, 2, 3, then the next pentamer, then 1, 2, then 1. So the pattern is 3, 2, 3, 2 for the stripe. If we just do the bending of pentamers, 2 pentamers binding together and then bend. If we just do the bending, it just goes up and comes back. There is no helicity. But why we are seeing that helicity? The reason for helicity is not just bending, it's also torsion. So 2 pentamers bind together, bend, and then there's a torsion. The second one, bind, bend, and then there's a torsion. And that torsion creates the helicity for it to go up. And the same story is for twisted tubes. But twisted tube, the pattern is different. So for twisted tube, the pattern is 1, 2, 3, again 1, 2, 3, 1. But it's, instead of 3, 2, 3, 2, here is 3, 3, 3, 3, 3. But the same thing, if it's just bending, there's no helicity. You just get a cup of protein. It doesn't go up. But here, if you add the torsion, it starts going down and then suddenly starts coming up. So that kind of shows that we need more when you're talking about nature, because they are rigid objects. These rigid objects, they cannot just bend easily, but they have to compensate for that by that bending and torsion to create what we are seeing. And then now the question, why only those 2? So we need that like kind of combinatorial analysis. So we say we have a dimer of pentamers, and then the next dimer either binds here, or here, or here, or here. So these 2 cases are identical to these 2 cases. For the top case, now we have dimers next to dimer next to dimer. So the second row of dimers either binds to the first row. If it binds to the first row, it creates those squashed hexagons that we were seeing in the flat tubes. So it has to give us a flat tube because it has the building block of a squashed hexagon. And it's hard to see, but it's a squash hexagon again. And if there's no contact between them, this is what we are seeing for the twisted tubes, that there was no contact. So it doesn't matter what method we choose, we either get a flat tube or we get a twisted tube. And the same thing for this case. So we have first row, the second row either binds here or here, and we get a squash hexagon, which this type of this local interaction was seen in the flat tube. And if there's no interaction between them, so again, it would be same as twisted tube, because then the next one can come and bind here. So we see that by just counting all the possible ways, we either get a flat tube or we get a twisted tube. So there's no other possibilities. And if we look at the tiling of them, so this is the tiling of the flat tube. That's when I was talking about squash hexagon is here. If you look at the tiling of it, if we just look at the pentagon for a flat tube and you open it, so you see the squash hexagon, squash hexagon, squash hexagon. And if you now, for the twisted tube, what you do, you remove this interaction and you replace it with this interaction. So that tiling, you rotate it, you lose this interaction and you replace it with this interaction. So then that gives you the twisted tube. So how you could shift from one tiling to the other tiling. And this is gorgeous, isn't it? So the twisted tubes are, as you could, I don't know, do you remember telephone cords in the past? Yeah, so they are like that. And they are really like that. They are flexible. They could be a really close bar and then they get farther. And the question of why, what's the reason for that nice behavior? We believe it's torsion angle. Because if you change the bending angle, it does that, but in a weird way. We think it's torsion angle, but we are now working on the data to see if it's really just torsion or a bit of bending angle is also changing, but they are quite flexible objects. And now at the end, so I just want to say quickly about the spherical particles that we are seeing in AaLS. So it's not just those tubes. We are also seeing some spherical particles. So again, the first thing for a spherical particle would be the classical coatings that pentagons, hexagons, or triangular. So probably we know about it. So if you were to Roydenstock, probably you saw them. So still here is fine. It works for lots of viruses, but it doesn't work for all of them. Like the MS2 is made of dimers. And for MS2, if you put pentagons and hexagons, you see that the monomer or protein subunits are sitting next to an edge. But over here, but for prokaryote, they are sitting next to a corner. That's, if you want to capture the position of protein, they have to be in an angle. They have to be located in an angle. So it shows that the Caspar-Cook theory, the Caspar-Cook way, doesn't work for MS2. So we need more tiling, which comes via tiling theory, which she's sitting there, came with all these ideas. Then over here, we need to use another tiling, which is the round tiling, which is then each dimer, we are using this round tiling, and now we see that each protein is sitting in the corner of our tiles. Or another one, which is HPV virus, is just made of pentamers, but all just pentagons, if you want to say mathematically. And definitely Caspar-Cook cannot work here. So over here, what she did with this virus, it was about looking into interaction instead of just the building blocks. Because in this virus, we have two types of interactions. We have 3 monomers next to each other in the kite one that we call it trimeric interaction. In trimeric interaction, one monomer gives an arm to the other one gives an arm to that, and that one gives an arm to this. So we have a trimeric interaction, and we have a dimeric interaction. 2 monomers facing each other. I give you an arm, and I get your arm. So there are 2 types of interactions, so which means that we need 2 tiles. And then when she used these 2 tiles, so now we could see that how we could tile the surface. And these have biological meaning. So now if we make a prediction based on these 2 tiles, it means that this is a viable option, which I think you also predicted a spherical particle using these 2 and, a tubular particle with these 2 tiles, and that was also observed in the experiments. But that's not the end of the story. They are, so Caspar-Cook, and then comes viral tiling theory, but this doesn't work for all of them. Like for example, here, this is a cage made for AaLS, form of those pentamers. If you look at these pentamers, one monomer is interacting, the other one is interacting, the other one, but one of them is doing nothing. And that's, till now, they have to do something based on quasi-equivalence. They have to do an interaction. Why one of them is just doing nothing? So now, because how can we make prediction for this type of spherical particles? So these have been observed in AaLS. So the experiments, they have seen these 4 spherical particles. What we do here, we are looking at the interaction network. What I mean by interaction network, we represent each pentamer or each building block or assembly unit or capsomer by the center of its mass, and we connect them if they are interacting with each other, and we don't connect them if they are not. But that gives us the interaction network. And now we look at this interaction network and try to make prediction based on this interaction network. So if you look at these 4 has been observed in the assembly of AaLS proteins. So we see that the interaction network here is just made of triangles. Here there are triangles and these squash hexagon, which we were seeing in tubular structure. So tubular structure was just squash hexagons, but here we have a combination of squash hexagons and triangle. So we know our local rules. The local rule is triangle and a squash hexagon. So now we want to make prediction based on these 2. So a squash hexagon can be divided into 1 square and 2 triangles. So it means that we have just triangles and squares, and we must be able to remove some lines to create squash hexagons and just triangles. So we know the local rules are triangle and squares, and we must be able to remove some lines to create squash hexagon. And this we need some tessellation made of these triangles and squash hexagons that has some repeat. So a tessellation that has some repeat, that's a tiling. That's a tiling. Now we have to go and check all the tilings, see which tilings they have this feature. So tilings we have uniform tilings. Uniform tiling means that each vertex is identical to all the other ones. For example, in this tiling, we call it Kagome lattice. Each vertex is surrounded by a triangle, hexagon, triangle, hexagon. Means that 3, 6, 3, 6. But that's how we are representing these tiling. K uniform tiling, it has K different types of vertices. So one vertex is surrounded by 3, 3, 3, 4, 4. The other one is 3, 3, 4, 3, 4. So we have two types of vertices here. We should call them, this is the two uniform tiling. We have 3 uniform tiling. I think up to 6 uniform tiling, they have been categorized all, but beyond that, not yet. So we just now go check all the tilings, that they are made of triangles and squares, and that we could remove some lines to create those squash hexagons out of them. But it's okay to have some extra squares at the center of a 4-4 symmetry, because if you remember, even in the Casper cube, you need to have an hexagon to cut around it, to cut 1/6 out of it. So it's okay to have a square which is the center of 4-4 symmetry, and then you cut 1/3 of it out when you're wrapping it up around the polyhedron. But they should be just the center of a 4-4 symmetry, not just anywhere. So we are allowing for having extra squares at the center of a 4-4 symmetry. Apart from that, everything should be either squash hexagons or triangles. So then the standard square tiling can be divided in these 3 ways. So around each 4-4 symmetry, we have 4 types of arrangements. And then if you start with type 1, then you have to continue with type 2. If you start with type 3, you have to continue with type 4, but 2 different ways. So we get these 2 beautiful tiles now here. But each of those colorful squares are center of a 4-4 symmetry. The other one is, that one is quite simple to divide it. You could just simply see that's the only way you could do it. The one that has a 6-4 symmetry, then you could see that one, it can be only divided in this way. So there's no extra way of dividing it. So we have just limited option of dividing all the lattices that they have this feature. So these are all the possible T1, T2, T3, and these 2. But now we have a lattice. We want to go from 2D to 3D. So we need to do the same thing, put a net of a polyhedron on it, cut it out, wrap it up, and then get the 3D structure. So the triangular tiling is fine, because it's just made of triangles. And then you could put a net of a icosahedron on it, cut it out, fold it, then you get the interaction network of the Y type 12 pentamers. So that one gives us a 12 pentamer. So can I do something bigger? Can I do it bigger? No, we cannot. Because if you do something bigger, then you're going to have a vertices of order 6. Means you're going to have, sorry. Yeah, I'll tell you quick. So you have a pentamer sitting on a 6-4 symmetry, which is not possible. Then we have, then the T1 here, but here we have 4-4 symmetry. So we have to put triangle, we have to put squares, net of a cube here, because we have this 4-4 symmetry. And if we cut it out, fold it up, so we get the 24 case. This kind of gives us a 24, predicts a 24. The other tiling is that one. If you put, because again, it's 4-4, means that you could just embed the net of a cube. If you put the net of cube, cut it out, fold it, you the 36 one, the one that has 6-fold symmetries. So for 6-fold symmetry, you could just do icosahedron net on it, put that net, cut it out, hold it, that kind of predicts 72 cages. So these are the one that has been observed in experiments. The T2 and T3 one, if I put the net on them and wrap it up, it predicts something with 48 and 60, which we also created the build file for them now. And we're just hoping that some experiments can show them as well in their experiment. So just wrap it up. That's what we see. 12, 24, 36, 72, they have been observed, and our method can capture them. 48 and 62 extra structure that the method shows they are possible. And we hope that they can be up. I mean, there are some things, the data hasn't published yet, but we have seen some other structure that kind of gives us a hope that this gap will be filled with these extra structures. But we know that now nothing more than 72 is possible. Nothing smaller than 12 is possible. So now we know that the range of possibility of the cages is that pentamer. So in conclusion, we develop a mathematical approach that can help us to understand the geometrical principle behind all those cages, experimentally observed nanoparticles, cage, tubes, or etc. So for tubes, we could see that why we are just seeing 2 cubes, what's the reason for helicity is bending and torsion. And for the spherical particle, we could see the one that they are seeing, and we could also predict extra particles that they are also possible. And then just at the end, about to say that what is related, why packing, why we are presenting in the packing, because I think these are important, because for packing, normally we just say that, what is the packaging, what's the package way of putting them next to each other, but nature has its own restrictions. So the pentamer has an R. These two interactions cannot just be 100%, it needs to be lower. And I think this is an interesting way of looking at it, putting more restriction for the packing to see that can we get what the nature is actually doing? Can we get those tubular structure with those restriction? Because I think yesterday they were showing the package way of putting pentamers. So for that, what we are seeing here is not the package way. So then why? Because there are biological restrictions. So then it would be nice to see if I put that extra restriction on it, then that would be the package one or not. These are like questions that could be answered with that, because we put them in, we rattle them and we find the best one. No, but it's important, I think, to have restrictions and then rattle it and then see what would be the best way of doing it. So at the end, thanks to IPSRC who is paying for me, and welcome to us pays for. I don't care about it. And right, and you scale Lucas, our collaborators, and thank you for your attention.